Sawadee crap, chemistry students of the world. Welcome to Passmark Chemistry, where I help you to pass your chemistry assessments. Today, we're going to be talking all about the full electron configuration of any element and how to work it out. Now, I'm going to try and keep this as tight, as concise, as condensed, as short as possible. So I'm not going to go into too much detail as to the full explanation of absolutely everything I'm going to say. I'm going to assume that you know a little bit about atoms and elements already, and if you want further information on any of the stuff we've talked about, then YouTube has loads of much better videos than this. But here's a fast way of working out the full electron configuration of any element. So hopefully by now we understand that elements kind of look like this. They've got their nucleus in the middle, and then they've got their electrons in layers around the outside. And the electrons are going around the outside of the nucleus. So positive nucleus, negative electrons around the outside. And that those electrons are moving in layers we're going to call shells. So this one has three shells, one, two, three shells of electrons. But hopefully by now we also know that they don't go in just nice, neat circles like orbiting around this nucleus. Instead, it's a little bit more kind of random than this. Now, the reason we don't draw it like this is because it looks like a mess that a toddler would make, but that's actually more accurate to the sort of route that an electron might take. Now, some very clever people, much more clever than me, worked out that it's not totally random, is that there is some kind of shape emerges when you watch the electron for long enough. And those shapes are called the orbitals. And those orbital shapes are quite distinct. So the smallest shape you could have, which is pretty much a sphere, so anywhere the electron's going to move within the sphere, and that is my s orbital. The next orbital shape is kind of like an infinity sign. I think sometimes they call it the dumbbell, and that is the p orbital. Then beyond that, I've got like a double dumbbell, and that is my d orbital. And I'm gonna do a really bad drawing of this one because it's a bit hard, but it looks a bit like a flower. There's just lots and lots of these infinity signs, makes the F. Now, to do with how they're orientated means that I have different versions of my P, D, and F orbitals, but we're just going to count them as one thing for now. Like I said, other videos will go into more detail. For us, and what I'm talking you through right now, is we're going to say that my S orbital is the smallest orbital, and it can only hold two electrons. So within that small little sphere, S orbital can hold two. My P orbitals can hold up to 6 electrons. My d orbital can hold up to 10, and my f can hold 14. A nice little mnemonic to help me remember my different orbital initials is I say that super people don't fail. If you want to be really cruel and nasty, you could say that stupid people do fail, but don't be nasty. Super people don't fail. So I have my s, p, d, and f orbitals, and they can hold a different number of electrons. But to work out the full electron configuration, I still have to consider the fact that they have shells. So, like I was drawing before, is that these shells that an atom might have, where the electrons are going, is that within these shells I have these orbitals. So within this shell I could have an SPDF, and then my next shell I could have SPDF, and then my next one I could have an SPDF. So the shells still exist, the layers of how far out my electrons are. It's just that it's not a circle going round and round, and that there's different orbital shapes within these layers. And where this gets a little bit more tricky is that not all the layers have all the orbital shells. For instance, the first layer only has an S. And where this gets even more tricky is the order that they fill in is not always obvious, but we'll get to that in a second. So if you look up in, say, in Scotland, if you're doing any of the SQA credits, you get a data booklet. And in your data booklet that's provided with you, you get it in your exam, you have a periodic table where you have the different elements and they'll give you an electron arrangement. So something like sodium is a 2-8-1. So this electron arrangement is not the same thing as a full configuration. What this arrangement shows you is the three layers of electrons in a sodium. So the first layer has 2 electrons, the next one has 8, and the outside one has 1. Now, how that matches up with what we are trying to understand about our electron configurations is that this first layer only has S, and that makes sense, 2 electrons. My next layer has a S and a P. So 6 plus 2 gives me the 8. And it has a third shell, but it's only got this one extra electron. So it's got its S and one electron around the outside, is the idea. If I wanted to know the full electron configuration for sodium and I was to write it out, then I need to know the order in which my electron shells or orbitals are going to fill. And here's the trick. This is one of the few things that's really important to memorize in chemistry. Chemistry is mostly about problem solving and knowing the rules and then applying that to different scenarios. But this I want you to memorize. So I've made a little chart to help me to remember how the electron orbitals fill. 1 to 7, 2 to 7, 3 to 7, 4 to 7. Now, technically, some of these further down orbitals don't really exist, but it just helps me to draw it out like this to remember. Now, the reason there's 4 columns is because I have 4 different orbitals. I have S, P, D, and F. And everything in this first column is an S orbital. Everything in the second is P, the third is D, and the fourth is F. Super people don't fail. So this is my electron orbitals, including ones that don't even really exist because they just keep going and going and going. Helps me to draw it out, like I said. But I'm going to fill up in this order. It would make a lot of sense to go, okay, I'm going to fill this one, then this one, then this one, then this one, this one, this one, this one, in a sort of order that makes sense going down the chart. But, you know, most things don't make sense in life. But we're trying to make sense of it. And if you follow this, you'll always be right. Is they're going to fill according to these diagonal lines. And what I mean by this is that, yes, my 1s is going to fill. So I go at the end of this arrow, I start the next arrow down. And then I'm cutting through 2s, so that's going to fill, and then fill down, and then down. So anytime I reach the end of an arrow, I start the start of another one, all the way down, all the way down, all the way down, to fill up for however many electrons I have. So let's do sodium as an example. It's sitting right over here. Is the full electron configuration for this is going to be a 1s, and s can hold 2 electrons. And then I'm going to get to a 2s, can hold 2 electrons. And then I get to the 2p, which can hold 6 electrons. And then I'm carrying on down to the 3s, which can hold 2 electrons. But let me just count. Now, all the small numbers up here, those are my electrons. My sodium has a total of 11 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, I've got too many. Now, it can fill up to 2 in that s orbital, but it doesn't mean they need to be filled. So I just leave that as a 1, and there we go. That adds up to 11. I have the full electron configuration for sodium. So they're filling in the order going down diagonally. Let's try a trickier one. Terbium. Terbium has 65 electrons, so a lot more than last time. So let's go through this chart and see if we can fill this up in the correct order all the way up to 65 electrons. So I'm going my 1s2, and then 2s2, 2p6, down to 3s2. So my next one is a 3p6, down to a 4s2, then to the 3d10, down to the 4p6, and down to the 5s2. After I'm on the 5s, I'm going to the next one, 4d10, then a 5p6. Round about now, I'm going to start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 30, 31, 32, 33, 34, 35, 36, 37, 38, 48, 49, 50, 51, 52, 53, 54. So I'm on 54. Might just make a wee note of that. Let's keep going. So I was on the 5p, which was the 6. Then I'm going down to the 6s2. And then I'm going to start my next one. A 4f goes up to 14. But I was on 54 before, so let's count again. 54, 55, 56, 57, 58, 59, 60, 70. So I'm 70. I'm too far. And we have 9 in this last orbital, because my 54, which I counted up to here, 54, 55, 56, plus the 9 takes me up to 65. the full electron configuration for terbium. So there you have it. I'm just following on down this lines to try and make the full electron configurations for my different elements. As long as I recognize that S has 2, P has 6, D has 10, F has 14, and please memorize that chart. In truth, this one doesn't exist, this one doesn't exist, this one doesn't exist either. But that's okay, because by the time you've counted up all these, well, you've reached the end anyway. So that's why I always just fill them all the way up. But that's our chart, that's our SPDF, and that's how I work out the full electron configuration. Thank you for your time, your patience, and attention. I suggest you practice yourself. Get yourself a chart out like that, practice drawing it out, pick any random elements in the periodic table, count up their electron configurations, and see if you're right. If you have any other suggestions for topics you'd like me to cover in Passmark Chemistry, then leave it in the comments section below. Thank you for all the comments and support. Abandon whatever reservations you might have about writing something, and do write something. It's nice. All right, I'll see you later. Bye.